Hi, so today we'll look at some other tests, including ratio, root, among other things, which tell us if a series converges or diverges. Before that, I'm going to briefly introduce the number e. The number e. I'm not going to go into as much details as the book, for the reason that while I think e is a very important number and you should know of it, the proofs given in the book are not very helpful in a way. They do not add anything to the discussion, and some of the concepts we have not covered. So I don't believe there's a reason we should cover the proofs right now. If you want to read about the proofs, it's in the book, and it's given in perfect detail. So definition: number e is equal to summation n is equal to 0 to infinity 1 over n factorial. Okay, so it has an infinite sum, and it is easy to see that this sum actually converges. Um, converges, convergent as Sn, which is equal to 1 plus 1 over 1 factorial plus 1 over 2 factorial plus dot 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 1 over n factorial, which is 1 plus 1 over 1 plus 1 over 1 times 2 plus 1 over 1 times 2 times 3 plus dot 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 plus 1 over 1 times 2 times 3 all the way up to n. This is strictly smaller than 1 plus 1 plus 1 half plus 2 squared plus 2 cubed plus dot 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 1 over 2 to the n, right? The denominators here are strictly larger than the denominator, strictly smaller than the denominators on the top series, and so every term in the bottom one is larger. Minus 1, not n. Okay, and this entire sum is strictly smaller than 3. Okay, so it's a monotonically increasing sequence which is bounded above, and so it's convergent. Okay, theorem. One of the first most interesting results about E that we are not going to prove in this course, but if we feel like it, we might come back to it later. For now, I'm not going to prove it. 3.31 is that limit n goes to 0, n goes to infinity, 1 plus 1 over n to the power n is equal to E. Okay? I'll give you a brief idea of the proof. The brief idea uses binomial expansion. Okay? Proof use binomial expansion. Expansion on Tn is equal to 1 plus 1 over n to the n. Okay? And you can show that limit n goes to infinity of Tn is smaller than or equal to E, is smaller than or equal to Sn, which is smaller than or equal to E. And similarly, you can show that for M, if n is greater than or equal to M, then limit n goes to infinity Tn is greater than or equal to Sm, which implies that as you take the limit of both sides, you get that what do you call limit Tn is equal to E. Therefore, limit n goes to infinity Tn is equal to E. Okay? This is the sketch of the proof. I'm not proving it in entire details. It's given in the book. I don't want to go into full details, but I just wanted to mention this theorem. And this has a very important consequence, which is theorem 3.32. E is irrational. Okay? Again, I'm going to skip the proof. I'm not going to prove it because it uses the proof of theorem 3.31, which I'm not covering. Okay? In fact, more is known. It's not just that E is irrational, it is actually not algebraic. Okay? And while we haven't gone into details of what an algebraic integer is, we did briefly talk about it for one of the homework questions. It is algebraic if you can write it as a root of a polynomial with rational coefficients. And as it turns out, E cannot be written as a root of any polynomial with rational coefficients. Okay? However, that's a much bigger theorem, and so we are not going to bother with it right now. Then we are going to look at the root and ratio tests. If you have taken Calc 3 before, you should be familiar with some of these in the naive version, which is just for reals. Okay? But now we are actually talking about this for complex numbers. Okay? First, theorem 3.33, the root test. Given summation an, put alpha is equal to lim sup as n goes to infinity of the nth root of the absolute value of an. Then we have the three following conditions. First, A, if alpha is less than 1, the series converges. If alpha is greater than 1, the series diverges. If alpha is strictly equal to 1, the test gives no information. It is inconclusive. Test is inconclusive. Okay, it does not tell me whether a series is convergent or divergent. Okay, proof. Well, if alpha is less than 1, then I can choose a beta such that alpha is, then there exists a beta such that alpha smaller than beta smaller than 1. Beta has to be real because otherwise you cannot make sense of smaller than. Okay? And there exists an n, which is a natural number, such that the nth root of a n is smaller than beta for every n greater than or equal to n. Right? Therefore, that is to say, a n is smaller than beta to the n for every n greater than or equal to n. As beta is smaller than 1, as beta is smaller than 1, summation beta to the n converges, as it's a geometric series. And now the comparison test implies, hence, summation a n converges by comparison test. Okay, this is proof of part A. For part B, the result is exactly similar. If alpha is greater than 1, then there is a sequence nk. So let me say something slightly different here. In the case A, I can talk about a beta existing where this condition is true, right? This condition being true for every n. If alpha is greater than 1, I cannot just reverse this condition because alpha is the supremum. Okay? Even if the supremum is greater, the infimum might be smaller. So terms might still be smaller regularly. Right? And so I can only talk about the supremum term, so I can't just completely reverse the argument. However, I can say that there exists a sequence n nk such that well, the supremum is alpha, so the sequence converges to alpha, such that nth root of a n k converges to alpha, right? Well, therefore, since alpha is greater than 1, infinitely many values of n are greater than 1, and n is greater than 1 for infinitely many values of a. Infinitely many values of n, and hence we do not have the condition that an goes to 0. Therefore, limit n goes to infinity, an is not equal to 0. Right? Which is necessary for convergence. Okay, if this limit is not 0, then the series has to be divergent. Therefore, is divergent. Okay. Now for the third part, um, we have to show that if the series, if it gives 1, then it is absolutely uh, inclusive, and we are just going to give you example. Uh, Consider summation 1 over n comma 1 over n squared. Both give both have alpha is equal to 1, but summation 1 over n converges, no, sorry, diverges, while summation 1 over n squared converges. As 2 is greater than 1 for the p-series test, or in, what was it, theorem, what theorem was it? 3.28, yeah, theorem 3.28 that we did last time. Okay. So that's the root test. Now let us look at the ratio test. Theorem 3.34, the ratio test. The series summation an, a, it converges if and only if, not if and only if, converges if lim sup n goes to infinity of an plus 1 over an is strictly smaller than 1, diverges if lim sup um, diverges if, not even lim sup, if just an plus 1 over an is greater than or equal to 1 for infinitely many values of n, which is to say for all n greater than or equal to n0. Can I say that it's for infinitely many values? Okay, this is definitely true. What I just said might not have been true, but this is definitely true. Okay, where n is some, where n naught is some fixed integer. In particular, this means that even if it's 1, it is diverging. Okay? Proof? That should not be true, though. Okay, let's look at the proof and see if I'm thinking, if my thinking is wrong. It could happen. So, if condition A holds, if A holds, then we can find B, beta smaller than 1, and integer n, and n such that um, n plus 1 over an is strictly smaller than beta for every n greater than or equal to n, which means, therefore, an plus 1 is smaller than beta times an, therefore an plus 2 is smaller than beta squared an, right? Which, okay, let me just say this. Beta an plus 1, which is smaller than beta squared an, and therefore an plus k smaller than beta to the k am an plus k an, right? For everything. Therefore, by comparison test now, therefore, by comparison test, the first finitely many terms do not matter. Whenever you are comparing series, the first finitely many terms is always just going to be some number, right? Some finite number does not affect if your final answer is going to be infinity or finite. So by comparison test, the eventual thing, it by comparison test, summation an converges as summation absolute value of an times summation beta as absolute value of an times summation beta to the n converges. Okay, it's just being multiplied by a constant. So it diverges. Now, for part 2, if an plus 1 is greater than or equal to an for every n greater than or equal to n0, it is easy to see that then limit n goes to 0, an is not equal to 0, right? Because if they're all greater than n0, then these values are going to be greater than n0, right? Absolute value of that has to be greater than n0, and even if the limit exists, the limit might not exist. It might go round, I don't know. But since this limit does not go to 0, it does not converge. It's not converge. Okay, so once again, a small note that the reason why things slightly confused me is note the limit n goes to infinity an plus 1 over an is equal to 1 does not give me, does not provide any information. For example, summation 1 over n, summation 1 over n squared. Okay? Same example again works. Okay? So let us look at some examples where you can use these tests. In general, whenever you can use ratio, so generally ratio test is much easier to use than root test, simply because computing roots is much harder. Okay? And whenever you can show using ratio test that something converges, the root test technically applies. Okay? However, there are times when root test is in a way easier than taking ratios. Okay? There are rare examples, but there are. Okay? So let us look at this. Example 1. Consider the series. Consider the series 1 over 2 plus 1 over 3 plus 1 over 2 squared plus 1 over 3 squared plus 1 over 2 cubed plus 1 over 3 cubed plus dot 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 dot. Okay? In this case, well, what is happening? Let us look at the ratios. Limit n goes to infinity of the infimum of an plus 1 over an is equal to limit n goes to infinity of 2 over 3 to the n, which is equal to 0. However, the lim sup n plus 1 over an is equal to limit n goes to infinity 3 over 2 to the n, which is equal to infinity. Right? Again, this time the lim sup is going to infinity. However, if we look at my ratio test, it does not say divergence if lim sup goes to infinity. It says convergent if lim sup less than 1, but divergent if it's greater than or equal to 1 for every n greater than n naught, which is clearly not happening because lim inf is going to 0. Right? So we cannot use ratio test meaningfully. Let us use a root test. Limit n goes to infinity infimum of nth root of an. In this case is limit n goes to infinity to nth root of 1 over 3 to the n, which is equal to 1 over root 3. Oops. Well, but we don't really care about the lim sup. We care lim inf. We care about the lim sup. Nth root of an is equal to limit n goes to infinity to nth root of 1 over 2 to the n is equal to 1 over root 2. And both of these are smaller than 1. Right? So as long as my lim sup is smaller than 1, this does converge. Therefore, root test indicates convergence. Ratio test does not apply. Test does not apply. So this is an example where you want to use root test and ratio test. The ratio test does not give you anything meaningful, right? However, the root test, which could be harder to find um, ratios for, still gives us the answer that it is actually convergent. Okay? Um, Similar example is 1 over 2 plus 1 over 8 plus 1 over 4 plus 1 over 32 plus 1 over 16 plus 1 over 128 plus 1 over 64 plus 1 over 256 right? Um, what is the pattern? Every second term is getting 64. 2, 4. Did I miss 8? You know what? Forget about this one. This is too complicated in a series. Apply. Whatever. This example is too annoying to write down, so I'm going to skip this. Basically, you're multiplying by 2. Okay, fine. I will just, because it is this annoying, I'm going to write it down. It's 1 over 8 for the 32 plus 1 over 16 plus 1 over 128 or 64 plus dot dot dot. Okay. What is idea? What is the idea? Where lim_inf goes to infinity, an plus 1 over an is equal to 1 over 8. Okay. However, lim_sup goes to infinity, an plus 1 over an is equal to 2. But limit n through to an is equal to 1. What is the idea? I am taking either I'm dividing by 8 or multiplying by 2. I'm alternating. First I divide by 8, then I multiply by 2. Then I divide by 8, then I multiply by 2. Effectively, in two terms, I am dividing by 4, which is why the root of whatever the change of every term is eventually 1 over 4. Square root of that over 2 terms is 1 over 2. The effective difference overall happening, the rate of decay is 1 over 2. Okay, so note, ratio test is easier to apply. But might fail more generally. Okay, but root test is applicable for a wider variety. Okay, so in theory, ratio test is a more specialized tool. When you can use it, it is extremely easy. However, if it can't be used, then well, that's it. Root test might be more annoying to use, but it can be used on a more variety of things. Okay, so there is a chance that ratio test will give you the answer for root test will not, but it might be much more annoying to do it. Okay, um, An important uh, result is that if the ratio test gives convergence, so will the root test. And if the root test is is inconclusive, then so is the root ratio test. Okay, so proof. More precisely, theorem 3.37. For any sequence Cn of positive numbers, for any sequence Cn of positive reals. So note root and ratio test, as I said before, hold for complex numbers also. However, they all have absolute values in everything. Okay, so while I'm going to state this theorem only for positive reals, that is because sorry, this is because whenever I take absolute value, it is going to land up as a positive real. Okay, so limit n goes to infinity infimum of Cn plus 1 over Cn is smaller than or equal to limit nth root of Cn, and the supremums are the other way around. Supremum nth root of Cn is smaller than or equal to limit infinity supremum of. Okay, in particular, if the limit exists, then the limit is equal. Sorry about that. Proof. Well, I'm not going to prove both ways. I'm just going to prove that the supremum of the root test is smaller than supremum of the ratio. Okay, the proof of the infimum is exactly the same, reversed. Okay, so I'm going to skip that. Let alpha is equal to limit n goes to infinity supremum of Cn plus 1 over Cn. Okay. Well, if alpha is equal to infinity, there is absolutely nothing to prove. If alpha is equal to positive infinity, there is nothing to prove. Prove. So let's assume that alpha is finite. If alpha is finite, choose a beta greater than alpha. Okay. What does that mean? Well, since this is a lim sup, then there exists an n such that Cn plus 1 over Cn is smaller than or equal to beta for every n greater than or equal to n. Right? Therefore, in particular, this means that, as we have seen before, Cn plus k plus 1 smaller than or equal to beta Cn plus k, which is smaller than or equal to um, beta to the k Cn for every k greater than or equal to 0. Right? Therefore, you could say that Cn is smaller than or equal to capital Cn times beta to the negative n times beta to the n for n greater than or equal to capital N. Just another way to rephrase the upper term. And this gives, therefore, the nth root of Cn is smaller than or equal to nth root of Cn beta to the minus n times beta. Okay? And therefore, in the limiting case, lim sup goes to infinity. Supremum nth root of Cn is smaller than or equal to beta. Okay? Because now, because what was I saying? Right. Now, because this is true for every beta greater than or equal to alpha, since this is true for every beta greater than or equal to alpha, not greater than or equal to, greater than alpha, we have lim sup of nth root of Cn smaller than or equal to, oops, not beta, alpha. Okay? The proof of the other way is exactly similar. For infimums, all the signs are reversed, and this is exactly similar. Okay? This is true by theorem 3.20 part B, which says, what does it say exactly? That this limit is equal to 1, as Cn beta to the minus n is a constant. Okay? So, in case you were stumped for half a second, as I was, honestly, this capital N is a constant, so the middle term is inside term is a constant, so the nth root goes to 1. So in the limiting case, it's smaller than or equal to beta. Okay? So these are my root and ratio test. Now, let us start looking at power series. And we'll look at some results related to power series and then stop. We won't go complete this section. Power series. Definition. Given a sequence of complex numbers, given sequence Cn of complex numbers. Um, the series summation n is equal to 0 to infinity Cn z to the power n is called a power series. Is called a power series. And the numbers Cn are called the coefficients. The numbers Cn are called the coefficients. And z is a complex number. Z is a complex number. Some of you might have seen power series before for real numbers. Here we are allowing them to be complex numbers. Okay? This is a direct generalization of what you've have seen before, maybe in Calculus 3. If not, then, well, this is something completely new. Term 3.29. Oops, 3.39. Given the power series, summation Cnz to the n, put alpha is equal to limit n goes to infinity supremum of the nth root of the n, and let r is equal to 1 over alpha. Okay? In that case, then summation Cnz to the n converges for z smaller than alpha, smaller than r, and diverges if the absolute value of c is greater than r. Okay? This r is called the radius of convergence. Note, r is called the radius of convergence of the power series. The power series. Okay? Proof. The proof is relatively simple. We are just going to apply the root test for the series. Put a n is equal to Cn z to the n. Okay? And apply root test. And apply root test. Well, what is happening? Limit n goes to infinity. Supremum of nth root of a n is going to be, well, nth root of z to the n is just z, absolute value of c, times limit n goes to infinity, supremum nth root of cn, right? Which is by definition alpha, which is by definition z over r. Okay? And now this converges if z over r is greater than 1, diverges if z over r, converges if z over r is less than 1, and diverges if z over r is greater than 1. Okay? Examples? examples. A, the series summation n to the n z to the n has r is equal to 0, right? If you look at n to the n, n through of n to the n is n, so alpha is equal to infinity. By definition, 1 over alpha is 0, okay? And so the radius of convergence is 0. On the other hand, the series summation z to the n over n factorial has r equal to positive infinity. Okay? And the idea being, if you use the root test again, you're going to have to do n through of n, n factorial, right? Which is about 1 over n, which goes to 0. So the supremum goes to 0, and the supremum is positive. So 1 over the supremum is going to go to infinity, right? So because we're only dealing with positives, we say that, oh, 1 over the supremum is going to positive infinity. Let's see. The series summation z to the n has radius r. Has radius r is equal to 1, right? So we have seen this before. This is basically the geometric series, right? And we saw that it converges if x was less than 1, absolute value of x was less than 1, and diverges if absolute value of x was greater than 1. In fact, for this series diverges even if absolute value of z is equal to 1. Okay, this is a special case because in this case z to the n does not go to 0, right? So diverges for absolute value of z is equal to 1 as z to the n does not go to 0, does not converge to 0. On the other hand, the series summation z to the n over n also has r is equal to 1, but it converges, it diverges for z is equal to 1, but converges for all other z with absolute value of 1. Okay, this is a hard theorem. This will prove later on, and not in this chapter. But this tells us that, as with root and ratio tests, things behave weirdly if the limit is 1. Okay? Finally, the series summation z to the n over n squared again has r is equal to 1, but it converges for all of them. It converges for all z with absolute value equal to 1. Okay? So the behavior of z when r is exactly equal to 1 or at r can be really weird. Okay? At R, it comes down to case by case analysis, and there are many different possible cases. Let's stop here. Next one would be summation by parts and absolute convergence. We'll look at that tomorrow. Okay.